Okay, welcome back. So last time we discussed a theorem about sum of two squares, which are due to Girard, Fermat, and Euler. And we said that if n is a sum of two squares of rational numbers, then uh, if and only if the sum is n is a sum of squares of two rational numbers, if and only if n is a sum of squares of two integers, and that happens if in the prime factors of n there are no prime factor of the form 3 mod 4. Either there are no prime factor of the form 3 mod 4, or if even if they're there, they should be appearing even number of times. So we can club them both as 0 is even, that the number of prime factors of the form 3 mod 4 should be even. So, and the proof, we gave elementary proof. So, if it was 3 mod 4, then if p is a square plus b square, then if it has a prime factor of the form 3 mod 4, then we saw that it divide the square of that also divides that number, and then that after dividing the square, it can also be written of the from again sum of two squares, and by descent will be done. On the other hand, to show it is a sum of, if it has the prime factors of the form 3 mod 4 are even appear even number of times, then we want to show it's a sum of two squares. So we can write it. It just suffices to show that the square free part is sum of two squares, and that is done by the square free part is 2 times some p1 p2 into pr, and then we use that if you have something is a product for each of them on prime of the form 1 mod 4 and 2, both are product of sum of two squares. And if you have, we use this identity that if you have product of two squares, product of sum of two squares, then that itself is the sum of two squares. And so the criteria is such that automatically it is, even if it is a rational number, then we can write as a mod sum of two rational square. Let's say a by c square plus b by c square, n equal to a by c square plus b by c square. Then n c square times n is a square plus b square. So the criteria for c square n is that c square n, if and only if that can happen, if and only if c square n has even number of factors of the form 3 mod 4, prime factors of the form 3 mod 4. So then the same holds for n. Whatever holds for c square n, the criteria being said it holds for n. So that was the proof. So then it naturally led to question, which will be the main topic here. Which integers are sum of, in this chapter, which integers are sum of two squares, okay? Which integers are sum of, so we saw which integers are sum of two squares. So the next question is, which integers are sum of two rational cubes? Okay, so which n in z can be written as n equal to x cube plus y cube for some x, y, and z? So today what we are going to do, we are going to delve into that question, but we are going to delve it, sort of see another motivation of this question. So we dealt with the square case, then which integer is sum of two squares of rational number. Then we are asking which integers are sum of cubes of two rational numbers. So these are called cube sum integers and or rational cube sum, and that is what we are going to study. But even before going that, we are seeing another, we'll be seeing another motivation of this from the point of view of Waring's problems. The simplest or the most classical case is that four square theorem. We saw sum of two square theorem, this is the sum of four square theorem. It's called Lagrange's four square theorem. That every integer n, so it is also their contribution due to Diophantus and the related results of Jacobi and so on. And there are even related on related topics, there are works of others, including Ramanujan. That every n in n can be written as n equal to a square plus b square plus c square plus d square. Okay, sum of four square for some a, b, c, d. So at most four squares. Okay, so every integer can be written as sum of at most four square. So for example, we have seen if p is a prime of the form 1 mod 4, in the last proof we have seen p can be written as sum of two square. Or some integer might be even a square. So that is included. So a, b, c, d are in n union 0. And this 4 is needed. For example, we know that 7, right? 7 cannot be written as a square plus b square plus c square, right? Because, yeah. So then A, B, C has to be like if like they can, none of them can be 3, but then it exceeds 7. So your choices are 1 and 2, and 7 is not a sum of two squares. So so you need 3, and even with 3, one of them can be 2, two of them cannot be 2. So then 2 plus 1 plus 1. So 4 is really needed here. Okay? And proof sketch is by Euler's force. So main idea of the proof is this Euler's four square identity and descent argument. Okay? So Euler's four square identity is the following, which says that if you have x1 square plus x2 square plus x3 square plus x4 square, so if you have product of two four squares, then they are again a sum of four squares. Okay? So this is what Euler's identity says, and it goes like this. So if you have one sum of four squares times another sum of four squares, okay, then that product is again a sum of four squares. So you have x1 square plus x2 square plus x3 square plus x4 square times y1 square plus y2 square plus y3 square plus y4 square is the sum of four square. First one is x1 y1 x2 y2 x3 minus x2 y2 minus x3 y3 minus x4 y4, and second one is x1 y2 plus x2 y1 plus x3 y4 minus x4 y3. Then x1 y3 minus x2 y4 plus x3 y1 plus x4 y2, and x1 y4 x2 y3 minus x3 y2 plus x4 y. So I've arranged it so that the first component is x1, second is x2, third is x3, and fourth is x4. So you know, with x1, once y1 will come, then y2, y3, y4. Then with x2, again y1, y2, y3, y4 all will come in like that. So it's modular sign. It's not that difficult to sort of remember, and each one will have exactly so if you have this identity, then it reduces to show that every prime p is the sum of four squares of at most four squares, right? So if p, so every prime you write their prime factorization, and yeah, so you can just in fact look at the square free part, and you have to express it as the sum of four squares. Then the integer itself is the sum of four squares, and that square free part is product of primes. So for example, if it is 2, then it is 1 square plus 1 square. If it is 1 mod 4, then it is already a square plus b square plus 0 square plus 0 square. But it could be 3 mod 4 like 7, and then you really need 4 squares. Okay. Yeah. So how do you prove it? So it reduces to, by this identity, reduced to show every prime p is the sum of four squares of non-negativity. Okay, so we use this Euler's identity, and then it reduces to show every prime sum of, so it reduces to show every prime p is the sum of four squares of non-negative integers. Okay, so if p is 1 mod 4, then yeah, so this I said, but a general like 7 I gave example. You need to show a sum of four squares. So how do you prove it? So for p, so first you show a multiple of p is the sum of four squares, and that is done by square counting. So you consider this set f equal to x square mod p, where x varies between 0 to p minus 1 by 2. So there are like p plus 1 by 2 elements, and these are all distinct. So these elements x square mod p will be distinct. So check that. And you have t minus 1 minus y square mod p, where y is between 0 to p minus 1 by 2. So this is also, so this is in bijection with minus y square, and this is in bijection with y square. So again, you can check that these are distinct. They're all distinct in FP. So in FP, you got p plus 1 by 2 and p plus 1 by 2. So p plus 1 element, but FP has only p elements. So each of this set S and T, so F is the definition, F and T is the definition. So S by definition is x square mod p, x is between 0 to p minus 1 by 2, and T is by definition minus 1 minus y square mod p, where y is between integer varying between 0 to p minus 1 by 2. As I said, p I'm taking to be odd, and this has p, so this squares mod p you can easily check, these are distinct. This minus 1 minus y square you can check is also distinct, and there are p plus 1 by 2 elements here, there are p plus 1 by 2 elements here. All of these elements are fp. So at least 2 of these elements total then p plus 1 elements, but fp has p element. So at least there's one element here and one element here, which the intersection, which is in the intersection. So I can say that x square is equal to -1 minus y square mod p. In other words, x square minus equal to -1 minus y square. So x square, if I bring it to this side, -1 minus y square. So x square plus y square plus 1 is divisible by p. So x square plus 1 plus 1 is equal to m times p, so for some m in z, and of course m has to be positive. So so further x is between 0 to p minus 1 by 2. So x square is strictly less than p minus p by 2 whole square, right? Because x is strictly less than p by 2 and y is strictly less than p by 2. I mean, y square is less than p by 2 whole square. So that means x square plus y square plus 1 is less than p square by 4 2 times plus 1. So this is less than p square because that amounts to saying that p square is greater than 2, which is the case. So mp, altogether you get mp is less than p square, so m is less than p. Okay. So what is happening here, that x square, let's estimate, we are getting x square is less than p by 2 whole square and y square is less than p by 2 whole square because of this. So m times p, which is x square plus y square plus 1, is less than p square by 4 plus p square by 4, which is p square by 2 plus 1. And because p is greater than 2, at least 3, so this is less than p square. So mp is less than p square, everything is positive. So you cancel, so you get m is less than p. So you get 0 less than m less than p. Okay. So 0 is less than m less than p. So there exists m such that m times p, where m is between 0 to p, so that m times p is sum of 4 squares, right? So m be the smallest positive integer, so that m times p is sum of 4 squares. Okay. So we saw there is an example of m which is less than p, such that m times p is sum of 4 square, namely x square plus y square plus 1 square plus 0 square. So let m be the smallest positive integer, such that m times p is sum of 4 squares. So there is such m, so choose the smallest. Okay, for so sum of 4 squares, so this is a1 square plus a2 square plus a3 square plus a4 square, where this ai are in z and 1 less than I less than 4. Right? So we know that 0 less than m less than p, and to show that m is equal to 1, we choose m to be the smallest, then m has to be, so that this, then m has to be equal to, so the claim is that m has to be equal to, so m has to be equal to 1. So if if m is strictly positive, so m is strictly greater than 1, then you produce another m prime, so that m prime p is also a sum of 4 square. So that is the strategy, and then you get in contradiction to the definition of it. So again, you do the descent. Okay. So the idea of the rest of the proof is to do descent. And if you choose the smallest positive answer, that m times p is the sum of 4 squares, and I claim m to be 1. If m is not 1, then I produce another m prime, so that m prime times p is also sum of 4 squares. So that contradicts the definition of m. And so we get our, okay. And to use the descent, so this is the descent method which we discussed last time. So we use descent together with Euler's identity to prove this step. Okay. So so it remains to prove this step, and I explain this now. So define Ri belongs to Z. Ri is between. Um, so so if you have AI, you divide them by m, and they call the residue to be R. So Ri is generally between 0 to m minus 1, and you sort of divide it. You shift it by m by 2. Okay, so you make Ri to be between minus m by 2 to m by 2. Just usual, you subtract by m by 2. Right? So you choose Ri to be between minus m by 2 less than Ri less than m by 2. And anyway, so you can always do this. It's a variant of the division algorithm. And Ri, so of course this Ri is an integer. Okay, you get that xi is congruent to Ri mod mi, and that's by construction. So then summation Ri square is summation ai square, right? So if you take summation Ri square, this is 0 mod mi. The same as summation mi square mod m, and that is equal to 0 mod m, because we had that summation mi square, summation ai square is 0 mod m, right? This step. So this is 1. Summation ai square equal to mp. So maybe I should write by 1. Okay, this step is by 1. Okay, so if so ai square is 0 mod m by 1, and ai square equal to ri square by definition of ri. So so there is m prime, so that m times m prime is summation ri square. This is again just from the above equation, right? Summation ri square is 0 mod m, so there is m prime and integer, so that m prime is this, and m prime belongs to n. So the goal is to show that m prime times p is also a sum of four squares. Okay, this m prime is our candidate, which will give us the contradiction. Now Ri is less than equal to m by 2, so Ri square is less than m square by 4, and m prime is by definition summation Ri square, right? So m times m prime is summation Ri squared. So that is less equal to m square, right? Because each Ri square less than m square by 4. So 4 times m square by 4, so this is less than m square. So m times m prime is less than m square. So you cancel m from both sides. So m prime is between 0 and m. So now suppose we'll show that m prime cannot be 0 and m prime cannot be n. Then m prime is strictly less than n. So why m prime cannot be 0? If m prime is 0, that means what do you get here from this? Summation of squares of real number is 0. So each Ri is 0 for all I. So that means m divides ai, right? So that means m squared divides ai squared, right? From this Ri square is equal to, from this, if m prime is 0, so a summation of Ri square is 0. That means each Ri is 0. So each Ri is 0, you put it here. That means m divides ai. If m divides ai, then m square divides m times p, right? Because summation, so this is 1. M times p is summation ai squared. So you are saying m divides ai squared. So m squared divides mp. So that means m divides p, and that is a contradiction, as m is between 0 and okay. So m square will divide mp. So mp is this. So m square will divide mp. And m will divide p by cancelling m. So m is less than p. On the other hand, the second case, m prime equal to m also cannot happen. So if m prime equal to m, that will mean Ri equal to actually m by 2, mod Ri equal to m by 2. Because Ri square is less than 4 times m square by 4, right? We did it here. Summation Ri square is less than summation, so each of them is less than m square by 4. So 4 times m square by 4. So they can at most sum it to m squared. And you are saying it is equal to m squared, right? If m prime equal to m, then you get this. This is equal to m squared, right? So each of them is less than m squared by 4. If one is less than, strictly less than m squared by 4, then the sum cannot be equal to m squared, right? It can only happen if each Ri is mod m by 2. Okay, so Ri is m by 2, that will mean m is even. So m is even, that will mean, yeah, here doesn't really matter. I think it won't matter, but yeah. So that will mean that because here I'm writing mod Ri equal to m by 2. So if this happens, that can only be happen if Ri is mod Ri is m by 2. So that can happen because each of these Ri square is less than m square by 4. I square is less than m square by 4. So each Ri square is, so each Ri square is less than 4, less than m square by 4. So sum of Ri square is less than m square. And so if the sum of m square, if m equal to m, and each Ri square is less than m square by 4. So if one of them is strictly less than m square, mod m by 2, then this cannot happen. So that means each Ri. So this is for all I. For I equal to 1, 2, 3, 4. Okay. So that means m is even. Now m is even is a problem because you have m times p. Now you go back to 1. So m times p is summation of 4 squared, and if m is even. So that means the sum of 4 squared is even. So then even number of them have to be even. So either all of them are even, or all of them are odd, or two of them are odd, or two of them are even. So either 0 of them are odd, or 2 of them are odd, or 4 of them, right? So that's what is written here. MP summation ai square is even, right? So only only an even number of AIs can be odd. So none can be odd, 2 can be odd, or all 4. 3 of them cannot be odd. Or exactly 1 of them or exactly 3 of them cannot be odd. Then the sum will not become even. So let's say A3 and A4 are odd, right? So then basically m by 2 works. So m by 2, then mp by 2 is A1 plus A2 whole square plus A1 minus A2 by 2 whole square plus A3 plus A4 by 2 whole square plus A3 minus A4 by 2 whole square, right? So you look at this, so this middle terms cancel, and so let's say A3 and A4 are odd, or A1 or A2 are odd, 2 of them are odd. Okay, so then or all 4 of them are even. So then you can carry it like this. So similarly, you can handle the other case. So that is the case. M by 2 into P is summation of AI square, where M by 2, what is AI prime square doesn't matter. But M by 2 is strictly less than M and greater than 0. So you got a contradiction to the fact that M is the smallest positive integer, right? Here M was the smallest positive integer. This contradiction to this, okay? So this was the contradiction, right? So it cannot be happen. This cannot happen. So this rules out what the other case. The two corners cannot happen. So you had 0 less than m prime less than this. So this equality is ruled out, and so is this equality is ruled out. Okay. These corners cannot happen. So basically, you can rule this out, and you can rule this equality out, and you can rule this equality. Okay. Okay. So that means 0 less than strictly less than m less than strictly less than. Okay. So as we assume 0 less than m prime less than. So then from 1 and 2, you have mp is summation ai square, and m prime p is summation m prime, sorry, what was that? Let's see, 2. mm prime, yeah. So sorry, prime is summation ri square. So you multiply these two things. Prime is summation ri square. Maybe I should write mp into prime, just so that there is no confusion. mp into m prime, right? So is this summation ri square, and this is equal to summation xi square, right? And why? Because of this star, right? This is the Euler's 4 square identity. If you have product of two 4 squares, then again, if you have product of sum of 4 squares, then it is again a sum of 4. Thank you.